Right, hello Precalculus students. We're going to go ahead and continue with week 2 here. This is Unit 8, Day 5. And last time we talked about, if you remember here, this was in class, we talked about a lot. We went through sections 1 through 4, which was all review. We talked about graphing functions. We talked about max and mins. We talked about intervals of increasing and decreasing. We talked about the step function as well and transformations of functions and some of the parent functions we went over also. We didn't do all these graphs here, but maybe we'll go back to those in class. I doubt it. We probably won't have a ton of time. But in class, we will just spend time probably looking at the worksheets if you've got homework questions or on the math space as well. So hopefully our class time won't be a full 45 minutes. I mean, it can be. It doesn't really matter, just if you have a lot of questions. But hopefully this lesson too is also shorter. I want to try to keep them relatively short. But this one's on continuity. So what is continuity? So we say a graph of a continuous function has no breaks, holes, or gaps in it. Um, and that means that you can basically sketch it without picking up your pencil. So a continuous function has no discontinuities. That's not a really good way to describe it. A continuous function is all connected. So connected would be a good word to use here. Um, okay, well, there are 3 types that I am going to expect you to know. The first type of discontinuity is infinite discontinuity. So that's the type where there is a vertical asymptote. So here at x equals c, there would be an infinite discontinuity at that vertical asymptote. Here, the next one is called a jump. Sometimes people just call this a non-removable. Same with infinite, it's also non-removable. But jump discontinuity is where there are 2 different levels from the left and right of the function. So here at x equals c again, there is a jump discontinuity. Sometimes people call this gap as well. We'll just call it jump. Um, Point discontinuity is the last one, and this one's also called removable. So infinite, jump, and point are what I'm looking for. Removable and non-removable are less important, but you may see those if you go further to calculus. So here we can see that there is a discontinuity, a break in the function at this point right there. It's a hole, and it's still discontinuous because we can't draw the whole function without picking up our pencil. We have to pick it up here and continue on the other side. So the function is discontinuous. Okay, well, let's go ahead and have a look at these here and give an answer. What do they want? They say, does the function have is the given function continuous for all x values? And they say, hint, think about the domain of the function. If not, what's the reason for the discontinuity? So the reason that we want to give is, I mean, we can give one of these types, but to be technically correct, there are three reasons why a function can be discontinuous, and we'll look at those in chapter 9. So right now, the answer is going to look fairly vague. We're just going to say probably most often the function's undefined or something like that. So let's go ahead and look at the first one. So this one is a cubic. Cubic graphs look something like this. So this one is continuous for all r, for all real numbers. So we'll just, let's say it says, if not, does the function given, I think we want to say is the function continuous at all x values? And then the answer would be yes here. So polynomials are continuous for all real numbers. Now, the inverse of a cubic is also continuous for all real numbers. It usually looks something like this. So this would be a cube root function. So the inverse of a cubic. And so these are also continuous for all real values. Here, the absolute value function looks like a V shape. There is no break or gap in it. I drew it with one swoop of my pen. I didn't have to pick it up, so this one is continuous. How about this one? This is the step function, and we've already seen it. So here, to graph a step function in Desmos, I think you have to use maybe floor. Yeah, there it is. So here's the floor function, and we can see that there's a lot of discontinuities, a lot of jump discontinuities. And so we could say jump discontinuity at each x in the integers. We'll use the double script z. So discontinuous, that's a DISC at each x in the integers. So if you look back at the graph, every integer, 1, 2, 3, 4, is where there's a new break in the function. So the greatest integer function is very discontinuous, lots of breaks in it. Okay, so how about the reciprocal function, 1 over x minus 2? That one looks like x minus 2, that is a shift to the right by 2, and then we'll drop in a vertical asymptote here. X equal 2 gives me a vertical asymptote, and then the function looks something like this. So you could say discontinuous. Is the function continuous? No. And then they say y. We could say x equal 2 is a vertical asymptote. And maybe let's just say something like infinite discontinuity. How about this guy right here? Let's factor the denominator, x minus 2 and x plus 2. And the x plus 2's cancel, and we're left with 1 over x minus 2. So now this is, so this cancellation right here, if you remember back from the beginning of the year, this implies a whole. And this one here, we saw from part E, so by E, this has a vertical asymptote at x equal 2. So this, we should be careful. You can't really just cancel a function like that. These two functions are no longer equal. In order to let them be equal, we'd have to say x can't be negative 2. So by the act of canceling here and removing that factor from the numerator and denominator, we've eliminated part of the information that was stored in the function, and that information is that x can't be negative 2 because of the denominator. That's yeah. So we have two discontinuities. So yeah, so this is a no, it's not continuous, and we could say whole and vertical asymptote, which give us the two types of removable and non-removable. So let's give them by their names. The whole is a point discontinuity, and the vertical asymptote is an infinite. All right. Part B says a summary about continuous and discontinuous functions. Continuous, no restricted domain. The domain of the function is all real numbers. So if the domain happens to be all real numbers, so we'll use the double script R here. If the domain is all real numbers, or negative infinity to infinity, then we usually say continuous. That's not necessarily the case, because right here, this one, the step function, has a domain of all real numbers. I can plug in any x value that I want, and it's going to return a y value, but it is not continuous. So it is the case, though, for most algebraic functions that as long as it's defined, it will be continuous. For example, polynomials are always continuous. The roots are all continuous on their domains. Let's see what else all the absolute value is. Even rational functions are continuous where they're defined. It's just where they're undefined is what we have to watch out. So examples, I would just say polynomials. polynomials roots. So roots I'll qualify by saying on their domains. And so rationals are discontinuous at certain places. I guess we could say absolute value of x. What other ones have we looked at? Yeah, I think that's good. Well, let's go ahead and throw in here sine and cosine. As long as there's no vertical asymptotes or break in the function, it's continuous. Now, discontinuous functions have restricted domains, usually have restricted. But that's not always the case. Like the square root function, for example, has a restricted domain and it's continuous everywhere on its domain. As long as x is not negative. If x is negative, then the function's undefined. So usually it's restricted domains like rational functions. So I'll say down here in examples, we'll say rational functions. So what do I mean by rational functions? Rational functions are these two examples, E and F. So we'll say examples E and F. Examples E and F from above. So that's usually rationals are written like this, where you have a p of x, a polynomial p of x divided by a polynomial q of x, and q is not 0. So rational functions fall in this category of discontinuous functions. So obviously we saw that the step function or the greatest integer function, so we'll say step function. Any vertical asymptotes, what's the other types that we have? Jumps and gaps. So I should also include here piecewise functions. Oops, I spelled piecewise. So usually piecewise functions have problems, not necessarily, like the absolute value is a piecewise function. So let me write that up here since I've already written it. So the absolute value is a piecewise function. It may not, just because it's piecewise doesn't mean it's going to have a discontinuity. It's x if x is bigger than or equal to 0, and negative x if x is less than 0. Now, you may have a piecewise function that looks something like this, where it's 1 if x is bigger than 0. Oops. If x is bigger than or equal to 0, and then maybe it's -1 if x is less than or equal or less than 0. So then there is a jump here. So it looks something like this. Let's switch colors. Here, it's up at 1 if x is bigger than 0, and it's down here at -1 if x is less than 0. So this is a common function. Yeah, a unit step function, but this is would be a jump discontinuity. So piecewise functions can often have discontinuities that look like this up here. This would be a piecewise. You could have holes and infinite discontinuity. So rational functions may have a hole. So we could say may have a hole. See how we're doing on time. Okay. Keep on moving here. So part C is talking about the domain and discontinuity of rational functions. So a domain for rational functions is really easy to find. You just want to find where the denominator is equal to 0. So in this case, so if we're looking for the domain, we're going to set the denominator equal to 0 and solve. By square rooting both sides, you want to make sure that you have both plus and minus. So plus and minus the square root of 9, which is just plus and minus 3. So these are the values that we want to exclude from the domain. So in interval notation, it would look like this, to -3, and then from -3 to 3, and then from 3 on to infinity. Now, this is a little bit tedious to write, so I would not mind if you wrote it like this, all real numbers, and then you just exclude the two values, plus and minus 3. That's fine if you want to write it like that. So, yeah, so what does this function look like? Well, at these 2 points, plus and minus 3, we have vertical asymptotes because the denominator is 0. So we'll drop vertical asymptotes at -3 and at 3. Now, they do say use a calculator here, but there's no reason why we have to. We were graphing rational functions without one at the beginning of the year, so we should be fine without it. If you plug in a number like 0 here for x, you'll find that you get 1 negative 1/9. So that's like right here. So at 0, it's negative 1/9. Now, to test on either side of the vertical asymptotes, you can either plug in a number like -2 or -4 to see into the function to see if it's positive or negative. So if I plug in -2 here for x, I'm going to get 4 minus 9 is -5. So it's going to be negative, which means that the function's going down this way at negative. Whoops, I plugged in -2, didn't I? So at -2, it's going down, so we can connect this point going down to -infinity. Now let's maybe check over here to the left of this vertical asymptote at 3. So we'll plug in 2, and again, I get negative. So I get a negative number of -1/5, so it's going to be going like this. Also, another way that you can look at this is we can look at the numerator here, and we see that the numerator, when I set it equal to 0, is never true. So no x values make it true, which means that there are no roots. So we could say no x-intercepts. Remember, to find x-intercepts, you set the numerator equal to 0. Now, taking the limit to left and right, the denominator has the highest power. Remember that Leghorn that we learned last time in class. So if the denominator has the highest power, the horizontal asymptote is at 0. So we can go ahead and put in a horizontal asymptote here. Now, functions may cross the horizontal asymptote, but because we already know that there are no x-intercepts, it will not cross the horizontal asymptote. If I plug in a number like 10,000 here, 10,000 squared minus 9 is going to be positive. So what that means is way over here at 10,000, comma, whatever, it's going to be a slightly positive number. So we can say that it has to be up here. It cannot be below the horizontal asymptote. It has to be above, because if I plug in a number greater than 3, I notice that it's positive. The same holds on the left-hand side here, so just like that. There we go. Number 4 is going to be very similar. So set the denominator equal to 0. Let's switch colors here. So x minus 1 equals 0, and x plus 6 equals 0. So we're setting the denominator equal to 0 here. And so that gives me 2 roots. So the 2 roots, roots of the denominator are going to be x equal 1, x can't be 1, and x can't be -6. So x is not 1 or -6. Let's drop vertical asymptotes at those 2 locations. Here is -6, and here's 1. And again, the denominator has the highest degree here, which is 2, and that means that the horizontal asymptote is going to be y equals 0. You can plug in a number like 0 if you want to test to see where the y-intercept is. In this case, the y-intercept is going to be -6 in the denominator. 2 divided by -6, -1/3. So we have a point right here. And since the denominator, or excuse me, the numerator is never 0. Remember, you set the numerator equal to 0. And if the numerator is equal to 0, that's where your roots are. Well, in this case, the numerator is never 0, so I don't have any x-intercepts. So this implies no x-intercepts. Okay, so that means that both of these, this point here cannot go up to infinity, or else it would cross the x-axis. So both of these have to go down. Now, we are, of course, neglecting, there could be a maximum or something inside of here that we're missing, but that's okay. Now here, notice that the multiplicity of these roots in the denominator is 1. The power is 1, which means that at that location, the sign will change. Now, you could also test it. So if I test something like 2 here into this function, I'm going to get 2 minus 1 is 1, and 2 plus 6 is 8. So this is positive, and this is positive, and this is positive. So it's positive here. The fact that it's positive is going to be up. So again, here, this one has a multiplicity of 1. The sign should change. If I plug in something like negative 10,000, this is going to be negative, this will be negative, and this will be positive. So it's going to be positive overall. Just like that. Now I think they want me to discuss the domain, or discuss the discontinuity. I mean, that's what this whole section's about. Doesn't say. So again, let's just maybe say infinite discontinuity at these points here. Maybe I should have written those infinite discontinuity. And then I can just move. That did not work. Okay. Here we go. Let's see if I can move these. Yeah. Okay. So these 2 points are where our function has infinite discontinuity. Same thing here. These 2 points are infinite discontinuity. Okay, these are, it's kind of redundant here, but this is more like review from the beginning of the year. But we'll go ahead and do this one. It's a little different. So this one we have, let's factor the numerator before we find the domain. So the numerator is x plus 3 and x minus 3 using difference of squares over x minus 3. The factor of x minus 3 cancels. And then we have y equal x plus 3, where x is not 3. So this thing, that the factor that we canceled here, it says that the denominator cannot be 3. I wrote negative 3. The denominator cannot be 3, or else it's undefined. So when I cancel this, when I slash this here, it disappears. And so notice I can plug 3 into this function, but we ought not to, because these two should be the same function. So I've just reduced it a little bit. So we have to write this x is not 3 there next to it, just to keep track of that information. So it's not a vertical asymptote here. This implies that there's a hole. So this is called removable discontinuity, or point discontinuity. So this is a point discontinuity. So the domain here is all real numbers without 3. X can't be 3. And so what is this? X plus 3. That's just a line. The slope is 1. So right here is slope is 1. And here, this is the y-intercept, is 3. So let's put the y-intercept right here, and the slope is 1. So we'll go this way, and here's x equal 3. This is where the hole is. Now, if you don't want to plot the hole like I just did, and you want to find the hole algebraically, ooh, that's really hard. Connecting the dots. Okay. If you want to find this hole's y value, which is 6, if you want to find it algebraically, you need to plug that x value that we are not allowed to have into the line. So that's going to be y at 3 is 3 plus 1, 3 is 6. So that's the y value. Or the other way to do it is to just plot points like I did until you get to the hole, and then just make sure that it's a hole. Okay, this one is similar. We have a hole at -5 and also a vertical asymptote at x equal 1. So we have x can't be 1 and x can't be -5. And so what's left after we do that cancellation? We have 1 over x minus 1, and x can't be -5. So this is just a vertical asymptote at 1. So let's go ahead and drop that in. And the denominator has the highest degree here of 1. So there's a horizontal asymptote at 0, just like that. And we could plug in, usually I like to plug in one point to the right of the vertical asymptote. It doesn't matter which one you plug it into. I'm just going to plug it into this one because it's more simplified. If I plug in number 2, then it's 1 over 2 minus 1 is just 1. And if I plug in 0, I get 1 over 0 minus 1 is -1. And the numerator is 1, so 1 can't be 0, so this implies no x-intercepts. So that means this has to go up here, and this has to approach the horizontal. This has to go down, and this side has to approach the horizontal. All right, great. Overall, where does each function have a domain restriction, discontinuity on the graph? How does this affect the domain of the function? So it has a discontinuity or domain restriction when the denominator equals 0. Or you could just say where the function is undefined. How does this affect the domain of the function? It's, well, wherever the domain is restricted, it has a discontinuity, and wherever, for rational functions, and wherever it has a discontinuity, the domain is restricted. Okay, I think that's sufficient for number 7 there. Okay, these last 3 problems here, it says find the domain of each function without graphing and discuss the continuity. So it's very similar to what we were doing up there. What I want to do is give the type of discontinuity and where it's at. So here, let's first factor using difference of squares. X plus 4 cancels, and we have x minus 4, and x can't be -4. So x can't be -4 because we did this cancellation here. And so this is a line, and lines are continuous everywhere except for this point is what we have. So the domain, all real numbers, x can't be -4. And the discontinuity is called, because we have that cancellation here, we have removable point discontinuity. That's because we removed that hole. So this was that hole there, and by canceling that out, in some sense, you are getting rid of the hole, and so we are keeping track of the hole with this comma, and x can't be -4. But yeah, so removable discontinuity. How about this next one? Let's factor the denominator this time. We have another removable discontinuity right here. And so after I cancel that, the function is going to be 1 over x minus 5, but we have to keep track of this root. So that factor was x equal -5. So x can't be -5. So what does this imply? We have a vertical asymptote, so that is infinite discontinuity. Let's write the domain first. So the domain, it is all real numbers x can't be plus or minus 5. Those are the two values. The denominator can't be positive 5, and here x can't be negative 5 because of that whole that we canceled. So the vertical asymptote is infinite discontinuity, so we'll say infinite discontinuity at, let's give a location, at x equal, should be 5 here. And now the whole is point discontinuity. We'll give a location, that's at x equal negative 5. That's the one that we canceled right here. Yeah, good. Okay, so 2 points of discontinuity on that function. Only one here. I didn't give a location. Let's give the location on this one. We'll say at x equal negative 4. Good. Sure. Let's do this one here, last one. Let's first factor to see if anything cancels. If nothing cancels, then it's just a vertical asymptote at x equal 1. And that would be infinite discontinuity, but let's see if it cancels. So this factors of positive 8 that add up to be negative 7. Maybe 8 and 1, but that's going to be positive. 4 and 2 is 6. I don't believe that factors. So it doesn't factor. So not factorable. If you're worried, which I am right now, maybe because I just don't know if I'm thinking straight. It's been a while since I've factored some polynomials. Maybe what you can do is plug it into the quadratic formula, just to be sure. If you get an imaginary value, then you know it's not factorable. So let's see here. So negative b plus or minus the square root of b squared, so that's a 49, minus 4 times a times c, so that's 4 times 8. 4 times 8 is 32. 49 minus 32 is 17. Oof. Over 2 times 2a, so it's just 2. Yeah, that's a pretty irrational value, so it's not no rational roots. So this is not factorable. Okay, so that means that we have infinite discontinuity. At x equal 1, the denominator. So that means the domain, I didn't write that down, the domain is all real numbers, x can't be 1. That's where the denominator is equal to 0. Yeah, there we go. So you should be able to do the homework. Let me show you the homework real quick. So we want precalculus. Here's the assignment guide. If you haven't already turned in these assignments on the week 1 Google form, please get on that. Hopefully you had most of this first chunk done. You might have just had to get worksheet 4 done. Worksheet 4 will be, I think all of these are all 3rd quarter grades. So all of those are going to be going on the 3rd quarter. This is 4th quarter grades. So 4th quarter, the grading is a little weird. 3rd quarter grading is normal, so this is pretty crucial to get this in. This will affect your grade, positive or negative. Everything beyond that point, of course, is just bonus. It helps your grade. It can't hurt your grade. So this is what I'm still looking for turned in afterward. Now, after today's homework, continuity of functions, I'm looking for worksheet 6 and math space. So I'll make sure to upload that math space right away. So that'll be up as soon as you are watching this video. All right, well, I will see you guys in class. Thanks for watching.